All right, scientific notation, specifically multiplying and dividing numbers that are in scientific notation. We're going to do that by applying the rules of exponents. What are the rules of exponents that are going to apply to multiplying and dividing numbers in scientific notation? When you multiply, you do what? Add the exponents of like bases, which in this case would be the tens, right? Because that's the only thing that has exponents in scientific notation. And when we divide, you subtract. Now we can still use the move things around. You know, if we had something times 10 to the negative 5 upstairs, sometimes 10 to the negative 8 downstairs, we can flip the 10 to the negative 5, 10 to the negative 8, and we can do it exactly like we would normally do it if we were dealing, with variables instead of powers of 10. All right, but here's the kind of the kicker. I teach scientific notation a little differently than you've been taught it before. And here's why. It always confused me the way it's taught in science. What was taught to me, I don't know how you guys were taught, but I suspect the same way I was taught. It's always confused me, and if you get the rules wrong, you miss a lot of problems. Right? You just do. So I want to kind of simplify things for you. All right, here's how I want to simplify things for you. Y'all ready? Mm-hmm. Small numbers, that communicates, right? Small numbers. What is a small number? What do we mean by small number? Decimals. Something less than 1 is a small number. Okay. Small numbers get negative exponents. So if we start with a really small number, that means I'm going to have negative exponents in scientific notation. If my scientific notation has a negative exponent, that means I'm going to have a small number. Okay? All right? Now, big numbers on the opposite side, and big numbers in scientific notation is any number bigger than 10, bigger than or equal to 10. Big numbers have positive exponents. And so you'll never hear me say, because we moved the decimal such and such direction, that means the exponent has to be positive or negative. We're not going to think of it that way in here. Right? Because the rules reverse if you're changing it from scientific notation or to scientific notation. The rules are backwards, and it's really easy to get them confused. This is not easy to get confused. Small numbers have negative exponents. Big numbers have positive exponents. That's it. The same rule works both directions. If we're changing it from scientific notation or to scientific notation, small numbers have negative exponents, big numbers positive exponents. Okay? So I want you to keep that in mind as we work our way through this. Now, what is scientific notation? Scientific notation is a method of writing very large or very small numbers, right? And here's what it looks like. Scientific notation is some number times 10 to a power of n. And then here are the conditions. A has to be a value between 1 and 10. It can include 1, but can't include 10. And n has to be an integer. That's all the positive and negative whole numbers. All right, so some numbers that you just really need to write this definition here, and that's just really, if you don't already know this, the important parameters right there. A has to be a value between 1 and 10. It can equal 1, but it can't equal 10. Okay? Now, here are some examples of some numbers. I want you to tell me if they're in scientific notation or not. 6.3 times 10 to the 17th. It is scientific notation, right? Is that a big number or a small number?
No, it's pretty big. I mean, it's big.
Why is it a big number? Because it's a positive exponent. If the exponent is positive, from a scientific notation standpoint, we're going to think of it as a big number. This is a pretty big number. It's going to have to move the decimal places 17, and we're going to move it in a way that makes the number Bigger.
Oh, yeah.
See how easy that is? All right, so if I'm making a number bigger, I would be moving the decimal this way.
Right.
Yeah, right? Because this is a big number. All right, what about this? Is this in scientific notation?
Yeah, it is.
No, it's not. You can't have zeros first.
What if you write in scientific notation?
Oh.
Why is it not in scientific notation? Because this number is less than 1, right? The A value has to be between 1 and 10. It can be 1, but it can't be 10. So this number is not in scientific notation. We would need to put it into scientific notation.
7 times 10 to the negative 7.
Wrong.
Negative
No,
9.
and see, well, which one is it?
9.
Right?
9.
You're right half the time. And that's what I want to think of it. Jack, this is why I want you to think of things as big numbers, small numbers. All right, is this a big number or a small number? Small number, so it has a negative exponent. What's the negative exponent going to be on this? If I put it in scientific notation, it would be 7 times 10 to the negative 1. Why is it negative 1? Because it's a small number. All right, negative 1 and negative 8 would give us 7.0 times 10 to the negative 9. Yeah, there. You add and keep the sign. Because you're multiplying, you add the exponents, right? Okay, so that's kind of big number, small number. I want you to kind of keep that in your mind. Big number, positive exponent. Small number, negative exponent. All right? Now, write this in scientific notation. Is it a big number or a small number? It's a big number. Big number in scientific notation is a number bigger than 10. 10 or bigger even. Because big numbers are going to have what kind of exponents? Positive exponents. So I know right now, positive exponent on my 10. I'm going to move the decimal 1, 2, 3, 4, 5. 8.56 times 10 to the 5th. All right. Now if I were changing this back into regular standard notation, it's a big number, so I have to make the number bigger. That's how I want you to think of it. All right. No right and left thinking. I don't think right, left. Because if you're changing it to scientific notation, you move it left. If you're changing it back out of scientific notation, you move it right. So positive exponent has no attachment to right or left. Sometimes it means right, sometimes it means left. I want you to think big number. Why is it a big number? Positive exponent. So make the number bigger. All right? I promise you, you'll love this after you get used to it. Big number or small number? Small number, right? So the exponent is going to be negative. Okay? The exponent is going to be negative, so that will be times 10. God, bless America. All right. 10 to some negative power, right? Negative what? 1, 2, 3.
Oh, no, 4.
4. So it's 5 times 10 to the negative 4. Notice, you don't have to think about which direction you move the decimal. It's a small number. The exponent has to be negative. All right? Now, if we're multiplying, I don't like this term right here, this coefficient. It's not really it's not really technically a coefficient because it's not multiplying a variable. We're going to multiply the numbers, and then we add the powers of 10. So the result is not, if the result is not in scientific notation, which sometimes it won't be when you multiply two numbers that are in scientific notation, you get a number that's not in scientific notation. You have to adjust it to make sure that it is. Okay? And then we'll use what we did in those few examples that we looked at the beginning. So let's have a look at this one. Somebody get out a scientific calculator. Got one close. Just one person. All right? We got it right here. Aspen's got it. So to multiply scientific notation numbers, you multiply the numerical part, then you multiply the powers of 10. What's 5.82 times 6.13?
35.6766.
35.6766. All right. Times 10 to the 14th. Why do we get 14 there? Yeah, the 11 plus 3. You're multiplying, so you add the exponents. Now, here's the question. Is this number in scientific notation?
No.
Why not?
Because it's bigger than 10.
Because this value is bigger than 10. It's a big number, which means it has a positive exponent. This number that's in front here is 3.56766 times 10 to the first power. Right? This part of it. Right? Has a positive exponent that's going to join this other positive exponent and give me 3.56766 times 10 to the 15th power. Now, do you have to show this step? No, you really don't. You need to know that you're moving it one place, and that's a positive change, right? Positive. It's a positive exponent because the number is big, right? Okay, so that gives you a positive exponent that joins this up, and 1 and 14 become 15. All right, now let's have a look at division of numbers in scientific notations. Again, you divide the numerical part, not coefficient, I don't like that. You divide the numbers and you subtract the powers. And we're going to subtract the powers, you know, kind of want to tell you again, we'll subtract differently depending on what we're looking at, right? All right. So 1.2 times 10 to the third over 9.6 times 10 to the negative, or times 10 to the sixth. Now, we don't really even need a calculator for this, because we know that 12 over 96 is 1/8, right? Because 12 times 8 is 9. So this, and 1/8 is 0.125. All right? And 3 minus 6 is -3.
Do you have to cross the line if it's like that, or do you just keep it like that?
No, we're just going to straight up subtract. If you're doing scientific notation, we're not going to cross the line, change the sign. We're going to just subtract and follow the rules of double signs. If you had a minus and negative, it would be adding to the top, those types of things. Okay? Why don't you pick that up? Yeah, just end that little thing. All right. Now, we've got a number that is a correct answer, but is it in scientific notation?
No.
It's not in scientific notation because the first number is not between 1 and 10. So I'm going to be taking this what kind of number?
Small.
Small, and moving it one place, and that's going to be a -1 scenario, right? So -1 and -3 would be -4. 1.25 times 10 to the -4.
Is this all we're learning today?
Yes, and you already know this.
Yeah.
But I really do hope that the big number, small number helps clarify your understanding of scientific notation. I always struggled with it. Oh, and if you move it right, this, if it's, but if you move it right the other way, it's this. So learning to understand big number, positive exponent, small number, negative exponent helps. Okay. All right. Let's look at this. Now this is telling us to find the quotient. We're really comparing these expressions with scientific notation. Which one of these looks bigger? Which one do you think is bigger right out of the box? One on the left, it looks bigger. It indeed is. It is bigger. And we can make that assumption, but this says find the quotient. So we're going to follow the instructions because part of the problem is telling you to find the quotient and then write the answers in scientific notation, and then we'll compare the two things. All right. Again, we don't really need a calculator on these because 72 divided by 36 is 2 times 10 to the second, right? And this other one, 105 divided by 35 is 0.3 times 10 to the second, right? Now, this one is in scientific notation. We're good, right? This one is not. We're going to be taking this, what kind of number is this? Small number, and moving the decimal one place, right? Small numbers have negative exponents. That's going to net me a -1 over here. That's going to be 3.0 times 10 to the first. Now, this is definitely greater than this.
Do we have to put the 0 behind the 2?
No. No, you don't. It's just kind of a, when I'm dealing with decimals and scientific notation, I kind of,
Automatically put it
yeah, I always make sure you have a leading 0 in science applications. And that's why I try to do that in here. All right, let's look at this one. This one is a little bit more involved, a little bit confusing. So let's just kind of take it apart. The speed of light is 3 times 10 to the 8th meters every second. Charlie, stop clicking, please. 3 times 10 to the 8th meters per second. That's a long way in 1 second. That's fast. The Earth is 1.47 times 10 to the 11th meters from the sun. That's a lot of meters from the sun. How many seconds does it take light to reach Earth from sun? Now, this is asking us, what is this? What unit is this? How many seconds? That is is it a distance? It's a time, right? So what we have here is a distance, we have a rate, and we have a time. Now, what formulas should that bring into play for us? Distance equals rate times time. So if we plug this in and we're solving for time, how do you solve this for time? Divide both sides by r. So the time here that we're looking for is equal to the distance, 1.47 times 10 to the 11th, divided by the rate, which is 3 times 10 to the 8th. That's going to give us the time in seconds, because the unit of time here in both instances is seconds. All right. Okay? Did y'all understand how I came to that? Now, you might have been able to draw that conclusion in some other ways, but I want you to, if you see distance, speed, and time involved in I want you to think distance equals rate times time. Common ACT type problem right here. All right, so we need to make this division. Aspen, you still got your calculator. What's 1.47 divided by 3? 0.49. That looks too much like 99. 0.49 times 10 to the third. Right. Now it says to express your answer in scientific notation. Right? Is that scientific notation?
No, sir.
What would we need to do to change it to scientific notation?
Decimal once to the right. And then
Which is it's going to be a small number, so that's a negative change, -1. Make that positive 2. 4.9 times 10 to the second seconds. All right, so that's 490 seconds. How many minutes is that? Divide that by 60. We get 8 and 10 over 60. 8 and 1/6. 8.2 approximately 8.2 seconds for light to get from the sun to the earth. That's pretty fast, really. So considering that it's 1.47 with 11, move the decimal 11 places, 147 billion meters. Light's pretty fast. Okay? All right, so no homework on this, but make sure you understand the concept.